Hi, this video we're going to look at homework 18 problem 3 on Webworks. It's regarding torsion. So let's take a look. In this video we're just going to look at AB section. Okay, so this is a bar that has been divided into 3 different sections. We have AB, BC, and CD, and there are 4 external torques applied to it. Torque A and torque B and torque C and D, and they give us all those value of those torques, and when you add up torque A and B and D, since they're the same direction, they should be equal to torque at C. And go ahead and verify it. 97 plus 85, then plus 107. Well, that's, let's see, 182 plus that will give us 289. That's exactly what we have at torque C. Okay, good. Then they told us this is made of this particular aluminum. And by the way, for this one, we need to know aluminum, what is going to be the yield strength for aluminum, and it's going to be actually yield share. Tau for aluminum for this one is going to be 180 megapascal for this material. Then they have a safety factor of 1.7 for my problem. Then from here, knowing yield strength, and which is going to be the failure stress, because at that time it's no longer elastic anymore, right? It can no longer get back to its original shape. So that's going to be set up as our failure strength. And then what will be our allowable? Allowable is going to be this yield strength over safety factor. So we will have 180 megapascal over 1.7. That will be allowable strength for this bar. And now, like we said, this has been divided into 3 different sections. If I were going to cut AB section, and we know, and we will know at AB section, and our internal torque, that's what we need to figure out, the torque during AB section, that's going to be just equal to TA, that's 97 Newton meter. And here I am not worried about the direction. And if we were looking at the BC section, if I were to cut anywhere between B and C, I can either look at the left side, which is here, and AB at the same direction, so the torque at what we cut is going to be equal to, so this is going to be internal torque at BC, it's going to be TA plus TV. That will give me 97 plus 85, that will give me 182 Newton meter, right? Now let's look at CD section. If we were cut randomly anywhere between CD, and the torque at this segment is going to be, I'm going to just look at the right section, it's going to be equal to TD, and that will be 107 Newton meter. Alright, so this is step we figure out the internal torque. Now we're going to use our shear stress due to torsion, and we know the shear stress tau is going to be equal to the internal torque at each section times the outer radius over moment of inertia, polar moment of inertia. So if I were just looking at the AB section and tau, here we want to see what's going to be maximum shear this bar is going to experience. The maximum shear is going to be equal to this allowable stress. That's as much as it can go, right? So because our tau here is going to be less than equal to this allowable. So maximum will have 180 megapascal over my safety factor, which is 1.7. And we'll have our T. For AB section, our internal torque is 97 Newton meter. And we know at the outer edge, we're going to experience the maximum shear, right? So the outer edge for AB is going to be the diameter right here. But it's actually now the diameter here is radius, so it's going to be half of D1, and my D1 is 20, so that will be half of the 20, and that's in unit of millimeter. Okay. Then J, well, this is hollow because there's a inner diameter. They ask you what's going to be the maximum allowable value for the diameter of the bore. So that's going to be basically your inner, that's what we are solving here, D bore. And then now let's figure out for hollow to polar moment of inertia is going to be half pi, and outer diameter, which is 20 over 2, it's going to be 10 to the power of 4 minus this radius of the bore to the power of 4, and that gives us unit of millimeter to the power of 4. Okay, so now we really need to look at our units, and let's see how do we go about it. And this is Newton meter, and how about we change that times 1000, then we will get Newton millimeter. So once we have Newton millimeter, millimeter square, and divided by 4, so that will give us millimeter square. And we know Newton per millimeter square is going to give us a unit of megapascal. So knowing that, the left side is megapascal, the right side is also megapascal. Then that's good. Then the only variable unknown is this radius, so we can solve this R. And if I were doing that, we'll have 180 over 1.7. We'll have 97,000 times 10. Then flip this 2 up there, so it will be 2. Then divided by pi, 10 to the power 4 minus radius to the 4. So here I'm going to isolate this. We're going to solve that. So 10 to the power 4 minus the radius to the power 4 is going to be equal to this 97,000 times 20 over pi, right? All those here, that's 20 over pi. And then we're going to divide this value. And to divide this value, so we're going to have divided by 180 over 1.7. I'm going to flip that 1.7 up. So we'll have that. And now let's take a look if we can calculate that. We have 97,000 times 20 divided by 1.7 over pi divided by 180. Did you get 2019.06 and 665? All right. And then we can go ahead and solve our radius. All right, so R to the power 4 is going to be 10,000. That's 10 to the power 4 minus this value. You just calculate it. Well, then, okay. Then I have 7980.93345. Then we're going to solve our radius, and will be power of 1/4, right? So we'll do (7980.9335) power of 1/4. Then I will have a radius of 9.451776, and that should be in unit of millimeter. And then your diameter of that bore will be times 2. We will get 18.9035. Okay, So that would be units of millimeter. And is this answer reasonable? Let's go look. Our D1 is 20. Okay, at least my bore size is not greater than that. Okay, so that concludes for this video, because you can use the same logic to solve the BC and CD, right? What's required in bore size for those two sections. So the only thing changed will be highlighted in this orange, because that's going to be the torque that's different, and this outer radius for each section is different. However, this value for tau, it's the same because it's the same material, but this is what you're solving for every single section. Once you get three values over here, and they ask what's going to be the overall, what's going to be the maximum allowable value for the overall, because they want to be the bore size here to be uniform distributed. So that would be the smallest value of all the three. Okay, all right, so that's all for this one, and I'll see you in the next one. Bye now. Well, this is a correction I need to make. I checked my numbers, and the calculation right here is not correct, and I'm pretty sure you already found out while you're following. And so the correct number for this calculation is actually, so I'm gonna mark it. Let me see, this is red. So this is not going to be that value. It's actually 5835.1. okay, so knowing that, that's going to change right here as well, and we'll change this value. That would be 4164.897. Then we're going to do power of 1/4. Then this will be 8.033, and then when we times 2, that's going to be 16.06686. all right, so that will be the correct diameter for that. I'm sorry about that, and this officially ends this video. All right, see you next one. Bye.